that we are going to have a look at has got to do with energy, the conversions of energy, and the concept of work and power. Definition of energy, it's an old one. You know it from grade 8. Definition of energy, the ability to do work. All right, now, when work is done, energy is always converted from one form into another. Can I use up energy? No, I can only convert energy. All right, remember, what does the law for conservation of energy tell us? Energy cannot be created or destroyed. I can only change its form from one form into another. Unfortunately, with every conversion, what happens? Some energy is converted into a useless form. All right. If we're going to have a look at the different forms of energy, mechanical energy is the sum of the kinetic and the potential energy of a body. It's just a new term, mechanical energy. All right, it is the sum of the kinetic and potential energy of the system. Kinetic energy, moving energy. Potential energy, stored energy in a stretched elastic, a spring that is compressed or stretched. Gravitational potential energy, object can fall. If it's high up, it can fall down. All right. And then the third group is just simply other forms of energy. That is kinetic energy, potential, and just other forms. Solar energy, sound energy, electrical energy. With every conversion of energy, some energy is lost. Well, it can't really get lost, but it's converted into a useless form. Now, we say no energy conversion is 100% efficient. So if I talk about efficiency, what am I referring to? How much of the total energy that I put into the system is used to do something useful in relation to what has become converted into a useless form. All right, that is what efficiency refers to. It's the ratio of the amount of useful energy in relation to the total amount. When you do the calculation, it's the smaller value over the bigger value. You can never get an answer greater than 100%. Okay? Because sometimes you don't know which one to use. If you don't know, just take the smaller value and stick it over the bigger one. That will give you the efficiency times 100 over 1 to get the percentage. No, it's a measure of how much work or energy is conserved in a process. Physics, quantity, work. Prerequisites. There must be a force to do work. Must be a force. The object must move, and it must move in the direction of the applied force. So, work done, it's an old definition. We need a force that is applied to the object. The object must move, but it must not only move, it must move in the direction of the applied force. So, if I hold this pen in my hand and I walk, am I doing work on the pen? Why not? Am I applying a force? Yes. Is the object moving? Yes. It is moving. But is it moving in the direction of one of the forces acting on it? No. So then it's not work done. All right. If I move it a little bit up and down. If I go up a step. All right. Work done. Force times distance. Work done is a W. Force is an F. Distance is an S. Remember the triangle. Work, force times distance. So what would distance be? Work divided by force. And force is work divided by distance. What other formula do we have for force? Mass times acceleration. All right. Sometimes they combine them in questions, these things. All right. So, if we have a change in energy, then there is work done. So, energy used or converted is equal to work done. The unit for work 1 joule equals 1 Newton meter. All right. Energy is in joule. Work done is energy used, so it's in joule. And how do we get an equivalent of 1 joule is 1 Newton meter. If I have a force of 1 Newton and it moves an object over a distance of 1 meter, I have expended 1 joule.
Win free airtime with One Africa TV. Share your comments on the channel. WhatsApp your feedback, name and town to 081 200 6659. One Africa TV. It just gets better.
Up the previous period with work and energy. Just sort of to revise very shortly, we said that work is done on an object if there is a force and if the object moves, but there's a third prerequisite. We said the object must move in the direction of one of the forces. All right. So, then if we do work, we convert energy. So all work done is equal to energy converted. Remember we said in the previous section that not all energy conversions are 100% efficient. Okay? We very often find that some of the energy is converted into a useless form. Usually heat, a little bit of sound, etc. Okay, now, when we started with energy, we said that we can break up energy into two main types, kinetic energy and potential energy. Okay, now, in terms of work being done, when I do work, I am converting energy and I'm either converting it to potential energy or some other form of kinetic energy. Now, if I lift an object against gravity, if I, for example, took this pencil case and I pushed it up, I'm doing work on the pencil case. The pencil case is moving because it's moving up. So the energy converted in this case has gone to potential energy because this pencil case has the ability to fall back down to the ground. Now, we can calculate a specific amount for potential energy. The formula that we use, EP, is mass. Mass is measured in kilograms times G, gravitational acceleration, or the force of gravity, has a force of 10 Newton per kilogram. So it's mass times 10 times the vertical height through which the object moved. For example, if I have a set of steps, okay, my steps are, let's say, 5 meters high and 7 meters long. I have a mass of 50 kilogram. What would my potential energy be when I reach the top of the stair? Well, our formula, E equals mgh. So my mass is 50 kilogram. G has a value of, remember it's a rounded off value, okay? And the height through which I have climbed is 5. Can you see I'm not doing work horizontally because there isn't a horizontal force as such. Okay, so I am working with a vertical height, so it will be 5. So 5 times 5 is 25, and we have 2 noughts. That is the amount of work done. That would be the potential energy gained by that person. Now, kinetic energy. Just like potential energy, I can calculate kinetic energy. Now, we've done a little bit on kinetic energy when we did, when we worked with momentum, and we had a look at elastic collisions. How do we know a collision is elastic? What must you go and look at? The kinetic energy before must equal the kinetic energy after. Okay, so how do we calculate kinetic energy? Well, the formula is half mv squared. Remember the half, it doesn't matter in which order we multiply. M times v squared times half, or m times a half times v squared. It just halves the whole thing once. Nah. All right, so when you work with this calculation, don't forget it is v squared. That's a common error you do. You write down the correct formula, and when you substitute into the formula, you forget to square the v. So take note of that. Now, here we have, they say kinetic energy is converted into gravitational potential energy, and then they say the total mechanical energy is conserved. Now, what is the total mechanical energy? It is the total energy of the system, implying kinetic plus potential energy. If I go and have a look at this diagram, the cyclist at the top of the hill over here, he has got potential energy. His kinetic energy at that point, if he is standing still, will be 0. When he reaches the bottom, he will have kinetic energy. Do you agree with me? And his potential energy is going to be 0. But the total energy of the system consists of kinetic plus potential. So, at any position along this path, the total energy is going to be the sum of the kinetic plus the potential energy. And the total amount of energy there will equal the total amount of energy there, will equal the total amount of energy there. Why? Because the law for conservation of energy tells us we cannot create or destroy energy. We can change its form. We are changing its form from potential to potential and kinetic, and as it goes faster and faster and goes lower down, the potential becomes less and the kinetic becomes more until it eventually has all been converted to kinetic energy. You following me? Okay. At any point along the path, the total mechanical energy is constant. Law for conservation of energy tells us we cannot create or destroy energy. Now, in the previous example, we had a bicycle at the top of the hill and it was driving down. Now I have a pendulum. And very simply, a pendulum is a device that changes gravitational potential energy into kinetic energy. If I lift up my weight that is suspended on this string and I let it go, it's going to swing backwards and forwards. Okay, now, at this point, it's got maximum potential energy, but how much kinetic energy will it have? Because it's standing still for a split second, it's got no kinetic energy. So there, the kinetic energy is 0. But as it starts falling, what is happening to the potential energy? The potential energy is decreasing, but what's happening to the kinetic? It's becoming more. So at this point, if we go and have a look at the total height through which the object falls, then at this point, he is going to have, well, if it's half the distance now, it doesn't look exactly half the distance, but if I work with the bottom of this and the bottom of that, no, it's not halfway. The diagram's not very good. If this height from there to there, if this mass piece was exactly here, half the height, what would I know about the kinetic energy and the potential energy? It would be equal. This diagram is slightly inaccurate. It's not this distance. All right? It is the vertical distance. If you work from the center of the object, then it's the vertical distance that determines the potential energy. All right. So, no. The object, the mass piece falls from that height to that height. So this is the distance through which it's moving. All right. Because weight works vertically down. All right. Okay. So, we will find then that if we look at this point, then the total energy is going to be the kinetic energy plus the potential energy. How would we determine the potential energy? mgh. Yes, we've got m, we've got g. We can work out, or if we have the total energy, we can work out the h, or if we have h, we can work out the total energy. All right. Right down here at the bottom, the ball is swinging with maximum speed. All right? So over here, all the potential energy has been converted into kinetic energy. And now the pendulum swings up. So what's going to happen? It's going to go slower and slower, goes fast, slower, and it's going to stop. Zero kinetic energy at that point, but maximum potential energy. And then it's going to go back again. All right. So this is very similar to that. At any place along the path that it's falling, the total energy is conserved. All right. Kinetic energy plus potential energy will give me the total energy. Although at the top, the total energy is potential because I have zero kinetic, and over here, the total energy is kinetic, I have zero potential, but anywhere along this path, I will add the two, and it must give me a constant value. Machines. Machines are devices for making work easier. We did a little section on levers. The machines are devices for making work easier. If I make work easier, do I necessarily make it less? No. And this is very important. When I do use a machine, I probably use more energy. But what the machine does is, it allows me to increase my strength. I can only, let's say, exert a force of 100 Newton. If I have a lever, it can multiply the force applied, and I can maybe lift a 200 Newton object. All right. So machines, they don't all have to be electrical. Okay. If I use a screwdriver to open up the lid of a paint can, that screwdriver is acting as a machine. Why? Yes, it's a lever. It's pivoting. It takes a small force over a long distance, and it converts it into a very large force to lift the lid over a very short distance. Okay, so machines, people, they don't make the amount of work less. It only makes it easier to do. How does it make it easier? We refer to an effort and a load. The effort is the force I apply. I'm trying to lift something. The stuff I'm trying to lift or move is the load. So what does a machine do is it usually multiplies the effort. It increases your force. So it takes your small force and it allows you to lift a large load, larger than your force. We will have a look at them. So machines are devices that allow the effort to be applied at one end to overcome a resisting force, the load, at another point. Machines, therefore, we say provide, the scientific term is a mechanical advantage. All right? We'll have a look at that. The mechanical advantage is the ratio of the load to the effort. Let's say I apply 100 Newton force, and I can lift a 500 Newton load, then load to effort, 500 to 100 gives me a 5-to-1 ratio for the mechanical advantage. If we assume no energy is lost, now is this completely true? No. Whenever I work with any machine, there is always some friction. So there will always be some noise, and there will always be some of the energy converted into heat. But when we do these calculations, just to make it a little bit easier at this level, we assume this machine is perfectly efficient unless they tell you. Okay, so if we assume no energy is lost or converted into a useless form, then the work done on the load side will equal the work done on the effort side. Just hang in there for a moment. Here we have our seesaw. You remember Bullet? You remember Charles? Okay. How can I balance that seesaw? Yes. He has a much greater weight than what he has. Let's say his weight is 800 Newton, and let's say Charles' weight was, let's just say, 600 Newton. All right? Both of these forces act over a distance to the pivot. All right? So, to make them balance, I must either push the pivot, see if it'll go. No. Almost. I must either push the pivot this way so that I can lengthen that part of the lever, or I can push him inwards to shorten his side of it. Do you understand? Because a large force over a small distance is equal to a small force over a large distance. That's the mechanical advantage. That's what a machine does. Now, all of the machines, now sometimes the distance isn't always that clear. But all the machines work on this basis. Small force acting over a long distance is equivalent to a very large force acting over a small distance. Yes? Yeah, but the machines also have levers and gears and pulleys, and they all function on this. Okay? Yeah, or they use hydraulics, but they have got some other machine, a device that multiplies the force. Okay? All right. So, where were we? Over there. All right. So, when we say work done on the load side will equal work done on the effort side of the machine, this is in terms of a large force over a small distance will give you the same value as a small force over a large distance. Okay. The ratio of distance moved by the effort to distance moved by the load is known as the velocity ratio. Now be careful. Here we have something called the mechanical advantage. Alright, here's the mechanical advantage. Sorry. Over there. The mechanical advantage is the ratio of the load, the stuff you're lifting, to the effort. The other thing that they refer to is the ratio of the distance moved by the effort in relation to the distance moved by the load. Can you see effort and load are now switched around? It's the load to effort. Yes. All right. I'll show you, I'll explain this in a moment, the velocity ratio. Now the velocity ratio, I can explain to you with something like this. If I have a gear, and let's say it's got, let's say 150 teeth. The front gear on my bicycle. Alright, here's my bicycle wheel on the back, and there's a cog on the back. So my chain goes there and there. This cog, let's just say, to make it easy, has 50 teeth. So, if I turn 1 revolution here, I am going to get 1, 2, 3 revolutions there. But this is going to be in the same time. This is the velocity ratio. I'm working slowly over here, and this one is going faster. All right. But if you don't look at it in terms of a small force over a large distance, small force over a long distance, larger force over a shorter distance. They are connected. Okay, it's just sometimes easier to see the velocity ratio in terms of the gear. That's why I'm explaining it like this. All right. The velocity ratio then is calculated by working with distance moved by effort. Here I'm pedaling my feet, all right? In relation to distance moved by the load, my bicycle travels 3 meters on 1 revolution of my feet. Yes, okay, so if we have 100% efficiency, then the mechanical advantage is always going to equal to the velocity ratio. Remember, mechanical advantage is load versus effort, and the velocity ratio is effort versus load. All right, because I have a small force over a long distance is converted to a large force over a short distance. All right. They say in practice, because we do not have 100% efficiency, the mechanical advantage is always less than the velocity ratio, not ration, ratio. Okay. This is because we have to do work to overcome the friction. I just want to see something for a moment. All right. Just this last section. Machines are force multipliers. Small effort lifts a large load, while other machines are distance multipliers. A lever is a distance multiplier, or a block and tackle. All right, a small distance on the effort side, large distance on the load side. For example, this one is a ramp, yes. If I have 1.5 meters high, and I want to lift up, let's say 3 meters. I can push a wheelbarrow up that slope. I can't lift it up like that. All right. So that one, the distance becomes longer in relation to that one. So the inclined plane is just a ramp, and then we have levers, pulleys, and gears, and I'll have a look at them in the next section. What I do want you to do. Yeah, okay. No, I think maybe stop at that point. Your homework is to make sure that you know the difference between the mechanical advantage and the velocity ratio. Because when we work with that and you don't know the difference, it's very confusing.
Shoprite is your home of low prices this Christmas with unforgettable savings on everything you need. Stock up this festive season with great deals. Like 2 kilos of Jungle Oats, only $49.99. And 2 kilos of Omaere, just $34.99. Don't miss out on unforgettable savings at the home of low prices this Christmas.